Good afternoon, everyone. It is a pleasure and an honor to have Dave Shafer here with us, visiting the college this week and giving us the colloquium today, the colloquium talk. Dave has been a designer of optical systems for the last 51 years. After working in industry for 15 years, he started his own one-person design and consulting company in 1980. He has about 150 patents for unusual optical designs and has published and spoken widely about new optical designs and design methods. Most of his work for the last 20 years has been for Carl Zeiss in Germany. His most odd business client was the surrealist artist Salvador Dali in 1980. Today, all state-of-the-art computer chips are made using a new type of lithographic optical system that Dave invented in 2006. One of Dave's novel telescope designs was on the Cassini spacecraft that went to Saturn, while other ones went to the asteroid Vesta and planetoid Sears and landed on a comet. Dave says that when he was born, his parents put a light bulb atop of him to keep him in peace, and since then he likes to work with light. Before we start, we would like to give you this certificate of appreciation, Dave, for being here with us. We really appreciate the time you have taken from your schedule to visit with us. And with this, let us welcome Dave.
Thank you. It's a pleasure to be here. Can everyone hear me okay? Okay? Yes. I have a friend who recently bought a new hearing aid. He says it's very expensive, state-of-the-art, the latest technology. I said, what kind is it? He says, 11:45. I'm going to be talking about some of the early years in my life before I actually got into doing design and how I got into optics. So my 51 years of design, that's working for companies, but I actually was interested in optics way before that. And as a kid, I always found magnifying glasses to be kind of like magic. It's almost a miracle. How do they do that thing that they do? And I used to collect magnifying glasses any time I had a chance to get one. I wasn't really interested in using it to see things like, bugs or close-ups of flowers or anything. What interests me is how does it work? How does it do that? And I grew up on a farm that it was very far from anything, so I didn't really have a way to get at equipment or optics, basically, so I had to make do. And one of the things I found is that some kinds of flashlight bulbs, little bulbs like this, not most of them, but some of them have a little lens on the tip. So I would take a hammer and break the bulb and get that little glass lens, and if you put it very close to your eye, you get about a 50x magnification. So I was using that as a magnifier. And I also made water drop microscopes, where you simply have a little pinhole, you put a drop of water in it, and you can get quite a bit of magnification, maybe 100x. The earliest microscopes from 300 years ago had a little glass lens, and that got up to about 250x. But you have to put it right up against your eye. There's no working distance. There's something sort of like this with no optics. It's just a pinhole. If you put it close enough to your eye, it has a great depth of field, and you can actually sort of magnify or use it as a magnifying glass if you have no optics. Now, I found out recently that the Sears Roebuck catalogs for the last 50-some years, they're all online. Some person has taken them, scanned them, and it's all up online. So a couple weeks ago, before coming here, I went online. I found the Sears Roebuck catalog from 1957 when I bought a microscope. And you'll notice the price, $5.67. This is a long time ago. It had 3 different magnifications. It had a turret with 3 different objectives. And I actually had 2 of them. One I used to look at pond water with amoeba and parameciums. And the other one I took apart to get at the lenses and use the lenses. At that time, I didn't know about Edmund optics, so you could actually send away and get lenses delivered to you. So I was looking for ways to get at lenses. So that's it. I don't have it anymore, but it's amazing how inexpensive things were back then. Of course, everything was cheaper. Now, I lived on a small farm, and we had 5,000 chickens. By now, I've forgotten most of their names. I'm sorry about that. And we had 1 cow, and I didn't drink pasteurized milk until I went to college. So one good thing about being on a small farm in the middle of nowhere is there's no light pollution. So the sky was very dark, and it was perfect for astronomy. So as a kid, I got interested in astronomy because you look up and you see all these, wonderful sights. Many people today have never seen a dark sky, a truly dark sky. I have some relatives that have spent their whole lives in a city. They've probably never seen the moon hardly, let alone, stars. So when you actually do see a very dark sky, it's spectacular, and it almost makes you realize that could be how religion got started. People saw these amazing things and had to come up with an explanation for it. I was talking once to the head of the planetarium division at Zeiss, and he said he was in Australia once, way out in the middle of nowhere, and he said the Milky Way cast a shadow. That's how dark the sky was. So when I was 13, I got a mail order kit from Edmunds on grinding a 6-inch diameter telescope mirror because I was interested in astronomy. And this sort of got me hooked on optics between the magnifying lenses, the microscope, the telescope. I got really interested in optics. This is not my telescope, but it looked something like that. It was a long time ago. Now here's a historical note. Very soon after the telescope was invented, something else was invented: window shades. I bought a small star spectroscope, which I still have. Back then, this is when I was about 14, it cost about $30. The exact same thing can be bought today, and it costs $300 to $400. So you can see inflation over time makes the prices go up. And I used it I made a slit out of 2 razor blades, and I looked at the sun and saw the Fraunhofer lines, and then I drew pictures of the absorption lines, which you can do. And one thing I found very interesting is there's some calcium lines in the ultraviolet that you're not supposed to be able to see because the eye is not sensitive to that wavelength. But you can see them. And the reason is the eye fluoresces at that short wavelength and re-emits at something that you can see. So I had a lot of fun with that. You can go blind if you do this long enough. I got these 3 books. These are later editions of them. They look different when I got them. Amateur Telescope Making Books 1, 2, and 3. And this was my Bible. I just devoured that with all the discussion of optics and telescope making. And I've read this several times. It's a wonderful, wonderful book about the history of the Mount Palomar telescope. It's full of amazing details. For example, the guy that was put in charge of figuring the 200-inch mirror, it took him 4 years. A lot of it was hand figuring with a knife edge test. And he had a big chart of 400 by 400 little grids. Do the knife edge test and go up and rub something, go back, look at it again. It took him 4 years. When he was finished, blew his brains out. The bullet did not hit the mirror. Wouldn't that have been something? A lot of interesting, strange historical facts. Anyway, it's a great read. Around then, I was just become a teenager, I found for the first time that men and women see the world differently. Quite differently. And I found that men are basically very simple with an off-on switch, and women are more complicated. Who knew? So I got an opportunity to go to the Cornell bookstore, and they had Conrady's 2 books, which I bought and started to read about lens design. There was almost nothing written back then about lens design. So I was very fortunate to be able to find these. And I also, another book, Southall's book, Mirrors, Prisms, and Lenses, which is written about 1890 or something, but it's still good today. And it actually has, well, I may go back to it later. Anyway, it's got complicated diagrams. And some of this was hard to understand because I hadn't had a lot of math, but I knew if I stuck with it, eventually it would make sense to me. I don't know if you've had that experience where you're reading and eventually the print just seems to fall off the page. But I've always been able to focus my attention very well and not be distracted. So I knew that with time, this would come to me, and I would eventually develop enough math to understand all this stuff. I love this where the joke is, the whole thing is in mathematics, and then so this is how some people communicate, is within a language that seems to be completely foreign to most people. Now, when I was in high school, there were no computers. There were no personal computers and hardly any mainframes, which a farm boy could hardly have access to. So I did a little bit of ray tracing the way people used to before computers, which is use 6-place logarithm tables. It's awful. It's very tedious. It takes a long time. It's very boring. And you wonder why anybody would ever want to do that as a profession, which people spend almost all their career doing these tedious calculations. It wasn't a lot of fun. So I did trace rays through a doublet, and that was enough for me. I said, okay, I get the idea. I don't want to do it anymore. But I knew I wanted to be a designer, despite that. And since there was almost nothing written about how to do design, there was nowhere to get help. And I love this cartoon. He says, Lassie get help. So Lassie goes to a psychiatrist and gets help. So I went to University of Rochester in 1961, and they had some mainframe computers, which is a big thing then. I mean, big in the sense of a new thing. And used punch cards for input. And the students at the Institute of Optics, where I was, were allowed to do some simple homework type problems using the computer. And they were, the insides of the computer was actual resistors and capacitors and, discrete things that you could see and hold in your hand. Nothing like, modern things on a chip. Now, back in 1961, all the freshmen were required to wear a beanie for 1 year. And that's me getting my beanie in freshman week. And 4 years later, I graduated in philosophy. I was a double major in optics and philosophy. Of the two educations, I've much more valued the philosophy than the optics, because if you learn how to think through a lot of philosophy training, that'll carry you much further than technical knowledge about optics. And I try to use philosophy a lot not philosophy a lot, but certain ways of thinking in my designs. Now, while there, I had an absolutely electrifying experience, which is I met my wife there. She was one of 4 generations of women. Her grandmother went to University of Rochester and I think got a PhD in mathematics, which is very unusual for women back then. Her mother went there in history, she went there in English, and her daughter went there in philosophy. So that's a lot of continuity. And that darn well better be my hand there. And she was able to see beyond my unsophisticated exterior to the equally unsophisticated interior. But somehow or another, she put all that aside, and we've been married for 52 years now. Now, during a summer job at 1964 at iTech, high-tech company in the Boston area, and I had 2 summer jobs there, once junior year, once as a senior year. It's a great idea for companies to sponsor that. They get to see somebody for a summer job and decide if that's somebody they might want to hire. You get to see the company, what it's like. And while working in the lab, I saw this weird thing of a spiral interference fringe. And Bob Shannon, who was my summer job boss, found this very intriguing. He came up with the correct explanation for it, and it was published in Applied Optics in 1965. And I'm one of the authors, so I got something published while I was still an undergraduate. That summer, when I found this, I was doing a lot of helium-neon interferometry experiments. I would come in the morning, and the helium-neon looked like a red laser. As the day went on, it looked more and more orange and dimmer because I was basically staring into a laser a lot. And because of this, I think I've become immune to high energy, and I often look directly at the sun, although not for long. Or, wait a minute, maybe it's the moon. Yeah. In the 1950s, there were electromechanical calculators. The thing on the left is called a Marchand calculator. It's got gears, and you plug it in. There's no electrical calculations. It's not a computer. It's simply electricity-driven gears. And it's probably there's probably a hand-crank version of it. Anyway, it could do multiplication, division to a considerable amount of accuracy. And people were doing ray traces using that as an aid. To an expert who had used that a lot, to get one light ray through one optical surface took about 3 minutes. As soon as, PCs came out, orders of magnitude improvement. And today, an ordinary, like this thing right here, can trace about 30 million ray surfaces a second. It's just absolutely phenomenal what's happened as far as the ability to do computations. The mechanical calculators were used in World War II to design bomb sites and various other military optical equipment. And they found very early on that women were much better at any kind of computations than men. They're much more accurate. So a lot of the early ray tracing was done by women. Now, before computers, any kind of optimization required matrix inversion, and to keep it at all practical, to do it by hand, it was just usually 2x2 matrices, very extremely simple, which you would do with a pencil and a paper, and you might have 2 variables like 2 radii and 2 aberrations, spherical aberration and comb or something, and you would just keep doing this in sequence. But today, everything is done not simultaneously, not sequentially. And I designed lithographic systems with several thousand rays, a few hundred variables, huge matrix inversion, and it takes a few seconds. It's just hard to imagine the change from when I first got started. Now, these early lens design programs, like Code 5, were not user-friendly. You had to very carefully study the program manual. That's probably about the size of the Code 5 manual. And every time you change jobs, you might end up having to use a different program, learn a whole other language. So it's kind of a big challenge to put up with that, basically. Now, my whole approach to design is, although I use a computer more than probably anyone's ever done before, use it all the time, I think design is best done by pure thought. If you want, especially if you want anything new and original, you have to come up with ideas that the computer's not going to. And one great thing about your brain is it's free, good for 2 shifts a day, user-friendly, familiar language, portable, time-sharing, color monitor, and there's no ads. So with some of the methods of design that I've developed over my career, I can think about designs and do it without a computer and know that I've come up with something that in principle will work once I get on the computer. And I found that the best way to be, and this applies to everything, not just optical design, anything in life this applies to, the best way to be creative when faced with any problem is to question hidden assumptions. We always are making unwarranted assumptions. Now, if you're given a problem to solve by somebody else, that person will usually make unwarranted assumptions when they construct the problem. For example, if somebody came to you and said, I want you to design a lens for me that does blah, 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 they shouldn't say that. They should say, I want you to design an optical system for me. Then I can say, well, it could be a mirror system, it could be a lens system, it could be a combination of the two. But when they say, I want you to design a lens for me, they're already putting an unwarranted assumption into the construction of the problem. And then I, receiving a problem, make a lot of unwarranted assumptions. Here's one example. As a kid, I bought an AM radio, and I made an unwarranted assumption. I listened to that for about a month every morning before I realized it also works in the PM. Not really. Okay, now we get to the heart of my talk, which is the purely career part. My first job after college, 1966, was at iTech. Small, high-tech company that mostly did classified military optics. Mostly very high-resolution reconnaissance cameras for the U-2 spy plane and early space satellite cameras. I also worked on a top-secret project there that was a new way to detect Russian submarines. And some years ago, this very secret technology was declassified over a period of a few decades, and today you can read all about it on the internet, and I'll go back and talk about that more in a minute. The atmosphere back then was the Cold War, and there was a lot of tension and uncertainty in the world over nuclear threats. And in the early days of the space program, there was a big arms race between us and Russia. Some of the early rockets didn't work. They blew up on the launch pad. This, of course, is from Mad Magazine. They don't actually do that kind of thing. But there was a lot of false steps in the early days of the space program. And we thought there was a missile gap with Russia. We thought they had many more missiles than we did. That was very threatening. And so there was a big push here to catch up. Now, it turns out they didn't have many more missiles. That was a mistake, and the way we found out about it is with spy cameras. The U-2 spy plane would, I forget how many miles, 7 miles up, 10 miles up, the pilot had to wear, oxygen, would take pictures of Russia and their missile sites, and we could start to count how many missiles, and it turns out they had many fewer than we did, not many more. Eventually, they did have a lot more, but in the early 60s, they didn't. One of the spy planes was shot down over Russia, a big international incident, and because of that happening, our government decided we're probably not going to do that so much anymore. We need to do it from space, where there's no chance of a satellite being shot down. And the Corona satellite program was started really, really super secret program where they sent a satellite up, go over Russia, take a lot of film pictures, and then the film would go into a can. The can would be ejected, fall down, and at a certain point a parachute would open up, and a plane with a hook at 500 miles an hour would catch it in midair. Sometimes they missed, and it would go into the ocean. This is what it looks like. You can imagine the timing had to be, I mean, I suppose if you miss it, you could turn around, but by the time you turn around, it would be down. So, and they were very successful doing this. It's amazing they were able to do this. So with that information from space, we knew that the Russians didn't have so many missiles. Now, the satellite was taking pictures that were actually stereo pictures. It had two different views, and photo interpreters would take that information and they could judge, for instance, the height of a building and a lot of useful information that would allow them to estimate how many missiles the Russians had. But the pictures coming out of these satellite pictures were distorted with different kinds of projective geometry distortion. So I had to design a lens for iTech that would undo those projective distortions and straighten everything out so it was a nice grid. And then those pictures, so in other words, they took the pictures and took pictures of the pictures and rectified the distortion. And then the photo interpreters would look in a stereo viewer and do all these useful things. And they made these, they worked 24 hours a day for 10 years straight, fixing up these things. So all this was very classified. Now back to the submarine project. When a submarine is, of course these days, submarine periscopes are quite different. They have basically something with a thin wire that carries digital information down. But back then it was all optical. And you can see the wake, little line there. If it's moving very slowly, there's a little line in the water, and a plane flying above can see that. Now in the early days, these are taken from World War II actually, there'd be guys on a lookout with binoculars scanning the water, looking for a flash of light that might be the sun bouncing off the front window of the periscope. Very unlikely you would see that, but you might. Or just if they could see something sticking up out of the water. And here somebody actually did see it. But if the water is not calm and as waves are like this, the sun bouncing off the waves makes all kinds of glimpses. And how on earth do you tell which is the periscope, if there is one, and which is just water reflections? Now from an airplane, you see there that wake is kind of big because the submarine is moving faster. And of course you would see the wake even if the water was not clear. Here it's clear. But if it's moving slowly, you might not be able to see it at all. What was needed was a new and highly sensitive way to spot submarine periscopes when they are above the surface of the water, even if they're not moving. And the solution was to use optics in this new and very top secret way. The technology was given back in 1966 the code name optical augmentation, and it's still called that today, and you can look it up on the internet. And this is how it works. We all know about Redeye from camera flash pictures. And Redeye is simply that light coming in is focused on the retina, and your retina is reflective. Not highly reflective, but it's somewhat reflective. The light reflects off the retina, comes back out of your eyeball, is collimated, and can travel pretty long distance without spreading much. So that's why, like your pet's eyes with a flash picture looks so bright. It's pretty much retro-reflected light. Here's what they did. Big battleship on the ocean sent a laser that would scan the horizon down a little bit above the water, like this. And the laser light would enter a periscope, go down the tube into the eye of the person looking through the periscope reflect off their retina, be recollimated out of the eye, go back up the tube, all the way back to the ship, and you could see it. You could see Redeye from kilometers away. And the collection area of the periscope was orders of magnitude bigger than the eye pupil. So a lot of energy was collected by the periscope, went into the eye, and you got a very strong signal back. And with that system, they could see a submarine periscope kilometers away. They used a near-infrared laser so that the person looking through the periscope wouldn't realize that they were being detected. The same technology was then applied to other situations. An airplane flying over camouflaged anti-aircraft guns, shooting a laser down, could get a retroreflection off the eye of the gunner and know there's something down there. From the ground, you can interrogate a satellite going over, satellite camera. You could even count the number of surfaces sometimes. Incredible technology. That's all back then. Now this is all declassified. For $100 on the internet, you can get this thing that you can hold in your hand. It's got a few LED lights, a little optical system. If you check into a hotel room, you want to know, are there any tiny little pinhole cameras hidden in the room? Or on a house, you simply look through this thing, and any camera will receive the LED light and it'll retroreflect back, and you'll see a bright spot. So this is like spy technology kind of stuff. And if you look at the internet, you will find you can buy smoke detectors that have a little hidden camera in it. So that stuff is out there, and some people want to know that they don't want to be viewed that way. So anyway, that's what happened to that technology. Now it turns out the countermeasure to defeat that system is pathetically simple and cheap. And back when I learned about the countermeasure, way back, the classification level was above top secret. And when you hear it, which you're not going to hear, you think, oh my God, it's so obvious. There is a very simple way to defeat it. And in general, most expensive high-tech systems, the countermeasure costs much less than 1% of the thing itself. So for example, this system here, this our so-called missile defense, it's totally bogus, doesn't work. This THAAD system that's supposed to be part of our missile defense, which we spent billions on, all the tests to date have been totally rigged. Totally rigged, where the incoming missile is saying, here I am, and it's sending out all kinds of signals. Despite that, most of the interceptions fail. And the reason is it's very hard to do that. It's very hard to successfully do this really high-tech thing of intercepting a high-speed missile. And it's not that hard to defeat expensive high-tech systems. Now this is just an example, the Tomahawk cruise missile. They cost like $3 million each, okay? The Navy has developed an extremely expensive high-energy laser for battleships and maybe for some ground-based things that will be able to spot an incoming cruise missile and zap it with a laser and burn it up, okay? That's the idea. Suppose instead, as a countermeasure, you simply make a reflective coating all around the outside of the cruise missile. How much does that cost? That'll reflect most of the laser energy away. I mean, that's just a simple example of how defeating something is always much simpler than constructing the thing itself. Now, I changed jobs in 1971, and I worked for a company that made infrared military optics. Part of that was early warning systems. If you're up in space and you want to see a missile coming over the horizon, the worst case is when the sun, it's the night sky, That's the Earth limb lit up by the sun, which is on the other side. You can't see the sun. The brightness of the Earth limb is roughly 10 orders of magnitude brighter than the signal you're looking for of a missile coming over. And what's key is to find some way to reject all that light that you don't want. And astronomers have a way to do that, because for a coronoscope, they want to look right near the sun, block out those many orders of magnitude of brightness from the sun, and look at the corona, which is much dimmer. And there's an optical system that does that, where the diffracted light coming from an aperture is re-imaged to a different place, and a smaller size aperture stop gets rid of a lot of the diffracted light. So at that other company, I did some space-based telescope designs that assume a front part that would block out a lot of this high-energy light that's right near the signal you're looking for, as well as just a lot of other systems. And I did a lot of mirror system design, which was very interesting to see what can be done with just a few mirrors. So at the same company, which specialized in infrared optics, I did some of these medical imagers, and it's amazing, with a thermal picture of someone's face, you can often tell if they're sick. And a few years ago, I was going to Korea to do work for Samsung. And when you get off the plane and you're entering the main airport in Seoul, there's all these passengers streaming by, coming into the airport, and there's 2 cameras in the hallway that you have, and they're infrared cameras looking at you, and they can tell if you have a fever, elevated temperature, and then they'll pull you aside and say, you know, maybe you need to be quarantined before we allow you to enter the country. So there's a lot of useful stuff that can be done with thermal imaging. My last company before I went on my own was Perkinelmer, and they were just starting to get into lithographic equipment. And this is the very early and extremely successful simple optical system they developed that made 1 micron computer chip features. And while I was there, I designed some further generations of that. Now, 1 micron, these early days, in fact, the handheld calculators, when those first came out, they had circuitry that had 1 micron features. It's really hard to picture how small is a micron. That little square there is a millimeter. There's the ant, a millimeter, and a micron is going to be 1,000th of that. You know, very small. This is an example of what nanotechnology can do these days. They can make these incredibly tiny things. This is the same size as a red blood cell. This is a cross-section of a human hair, and that's 1 micron, that little dot there. So back then, this is like 40 years ago, that was big stuff, circuits that were 1 micron. These days, that's like, you know, forget it, that's nothing. And today's state-of-the-art circuit features are about 30 times smaller than that. This is the edge of the human hair. Here's bacteria, human chromosome, and 3 nanometers, or 30 nanometers, I guess, is about 1/3 of that separation. So it's incredibly small. It's hard to even conceive of something being that small. It turns out that you can actually, well, I'll get to this later, but on something the size of the red blood cell, you could print a very good picture of yourself, or write a memo or something. That kind of small features can do amazing things. I also worked on laser fusion, very early days of laser fusion. And laser fusion is one of the biggest boondoggles of all times. If it ever works, which it won't, if it ever works, it's about as cost-effective a way of producing power as going to Mars to get sand for your kid's sandbox. It's just if laser fusion works, it's going to generate a lot of radioactivity, which they don't like to talk about. It's going to be incredibly expensive and requires absolute state-of-the-art technology and optics. That's not the way to efficiently generate power. But it's kept alive because they found it's a very effective way of testing out new atom bomb designs. They can have a tiny little miniature example of a new idea about bombs, and they can test it out at the focus of the laser fusion system. Now, the early days, when I got involved, they had two very intense laser beams coming in, and the light was focused down by highly aspheric lenses to a point, would go up to these conic mirrors and hit a target pellet at extreme angles because they wanted uniform illumination of the target pellet. Target pellet was about that size, filled with tritium gas, and they wanted to heat it up to 100 million degrees to get ignition, fusion ignition. So the problem this system had was the power was so intense that the fused silica aspheric lenses, despite being the purest that was obtainable, would absorb enough energy they would often explode. And they were extremely expensive. So they were looking for a new idea, and that's where I came in. I realized that with a third reflection, with an extra reflection inside the cavity, you could greatly reduce the speed required of those two lenses, greatly reduce the thickness as far as energy absorption, and greatly reduce the asphericity. So that was built, and that's a long time ago. Now we have like hundreds of beams in today's laser fusion system. One of my first patents from 1977 was an unusual kind of telescope that only used spherical mirrors. And the reason that the space programs liked it is several reasons. One is it's cheap because there's no aspheres. It's extremely insensitive to tolerances for various reasons. It was unobscured and had good image quality, and that later went to Saturn and various other places. This was a picture taken of Vesta with one of my telescopes. It was on the side of the, over there somewhere. And of course that crashed a few weeks ago into the Cassini into Jupiter. The Sears planetoid was very interesting. When they started to get close to it, they saw this very mysterious thing. I don't know if you followed this in the news. This is from maybe 2 years ago. These bright lights. Everybody said, what are bright lights coming from a planetoid? Is there like a city down there? And it took a long time. The closer they got, the more mysterious it was. And there was all kinds of different theories, such as aliens. I think today's consensus is that it's highly reflective, like liquid sodium. It's a lake, maybe, of liquid sodium or something. I don't buy that. I don't think it's aliens, but I don't think that's the right explanation. And then another one, once the Cassini was working well, if you get something up in space that works well, they never want to change it, because one of the things you want to do is reduce risk. So if something works, you do it again next time. So there probably will never be a different design than mine to go to these places because it seems to work well. So that brings me up to my middle years. When I started my own company, 1980, and the Apple II computer had just come out. So I was able to actually buy a home computer for the first time. Very primitive design program, early version of Oslo, and I did a lot of work for high-tech companies like Tropel, Ultratech, and Perkinelmer, using this primitive equipment. And since 1980, I've worked at home, which is not for everybody. Death working from home. You just tap, 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 and delete, delete, delete. Around that time, I did a very short but interesting project for Salvador Dali, who became famous by being famous, basically. He was a genius at self-promotion and would have great quotes. For instance, he says, "I don't do drugs, I am drugs." And he would get these pictures taken of these outrageous things, like working at his desk, or his lobster telephone. I mean, these things are ridiculous, but the press loved it. You know, something interesting to show. And so he was extremely well known. Now, he had mastered, late in his career, the ability to paint stereo paintings, by which I mean, this is what he looked like when I met him. He was, you know, an older person, but tack sharp. I met him in New York City, and I was along with him for about 1 hour discussing stereo ideas. And this is one example. He would paint a left-hand view, left-eye view of a scene, and a right-eye view. And there's actually 8 different depth planes here. And if you're able to cross your eyes, which I can do, and and fuse it, you can actually count the different levels there. So he had these paintings, and then he wanted a device that would allow people to view it. And that's where I came in, a new kind of stereo viewer. And I was always interested in stereo. When I was a kid, I had a ViewMaster. These things are still around. And one of the things that I've always been impressed with is no matter how simple a situation is, there's almost always more than one solution. So, for example, the obvious way to do a stereo viewer is you've got something in front of each eye, and there's your paintings, and you simply deviate the line of sight. I mean, how could there be something other than that? Well, there is something other than that. Namely, this. Who says they have to go like that? You could cross. Now you might wonder, what's the point? Well, there actually are situations where this has a certain advantage that this doesn't. But you have to remember, if you're going to do this, you have to remember to switch the order of the paintings. And if you don't, that's what you get. And it feels like your eyeballs are being sucked, your brain's being sucked out of your eyeballs. You get a terrific headache. So one approach would be simply prisms to deviate the line of sight, but prisms have a lot of color and are not adjustable. They wanted to be able to adjust for different distances from the paintings. And I realized that a 90-degree prism, there is a ray path through a right-angle prism that has no color at all. It's equivalent, because of the reflection, it's equivalent to a parallel plate that's tilted. You get no color, you get no distortion, and it's adjustable, and then as you tilt it, it makes the things deviate. So that was my solution to the situation. And the final viewer had a hinge so that you could actually fold it up and put it on a desk, pick it up, unfold it, and look at the stereo things. Another project, some of these are short-term projects, a astronomy club in Wales in the, what do you call it, the British Empire, whatever you call that thing. In Wales wanted a new telescope, and I had designed an extremely simple thing that would be great for amateurs, which is 2 spherical mirrors and a thick meniscus lens, sub-aperture corrector, and it works very well over a small field. And so I designed a version of that for a 20-inch aperture, which was then made by this club, and went into this observatory, which of all places is right on the ocean. One of the worst places for seeing. It's right against the water. So it was very simple to make. 2 spheres, a plano-convex lens and a plano-concave lens with the same radius, and it's in use today. It's the largest telescope in Wales, which is not a big deal. But now, a big jump up in size from that is this 30-meter diameter telescope that's supposed to be built in Hawaii. And that is part of a series of ever larger telescopes they keep talking about. Very large telescope, extremely large, but eventually you run out of money and you're not able to keep moving down the chain here. But I love the titles of these. And about a week ago, I came up with something that's actually down in this region, which is a new design. It's only 2 surfaces but 3 reflections. It's 2 conic mirrors, not high-order aspherics or anything, just simple conics. Has incredible performance. And this is a design for a 100-meter aperture. But it was so good in performance, I said, well, let's see, let's get a little more ambitious. So I came up with my Kilometer Scope. It's 1 kilometer, f1 primary, and with just these 2 surfaces, it's diffraction limited over a 4-meter diameter image. You couldn't even begin to use an image that big. And I don't think we're going to get funding for that. Now, the one in Hawaii, which is huge, 30 meters, has a spectroscope that goes with it, which is also huge. And for that, I designed this, which looks at the spectrum coming out of the prisms. They've since changed a lot of the parameters, so this is no longer relevant. But it's 6 freeform mirrors. And it has the kind of performance they were looking for. And since it's all reflective, it works for any wavelength. Okay, now we're getting to something that's a little bit more zero-order optics. We all know these door viewers. And the way they work is your eye is here, inside the door, and the rays are bent to a very wide angle outside. So this is the outside of the door. And you can look up, you can look down, you get this great thing. But people can't look in. Now, why can't they look in? The reason is very simple, is your eye is way too far away from being able to catch this big angle. You would have to somehow put your eye inside the system in order to be able to see any of these rays. You can imagine all you have is a little angle here. It turns out it's a tiny fraction of a degree compared to the 110 degrees that they're seeing. And that's the reason you can't look back in. But some years ago, about 1990-something, I realized there's a way to put your eye effectively inside that system such that you could look through. And it's simply, you can actually buy it these days on the internet for about $40. It's something you put up against the outside of the door. It looks like this. You put your eye there, and you can see right into the room. Okay? I actually have one here. And the sad part, from my point of view, is I thought, this is a great idea. It turns out you don't have to design anything. You don't have to buy anything. You have to make anything. You already have what you need, which is a binocular. You simply look through a binocular backwards. I see I'm sort of running out of time, so I'm going to move ahead here. This is how a binocular would work if used backwards. You put your eye at the objective. This is an unfolded light path. This is supposed to be the prisms and stuff. If you put your eye at the big end, the optics, the eyepiece forms an image of your eye over here out in space, about 10, 12, 15 millimeters away. So you simply move that system up to that, and this pupil here is moved to be inside there, and you end up getting about a 10-degree field of view inside the room. Anyway, so I got one here, and it works. Police use it, firemen use it. They might want to see, going down a hallway, if the building's on fire, is there anybody in this room? It doesn't have the field you would like. 10 degrees is not great, but it's better than nothing. Okay. Most of my work for the last 20 years has been lithography designing these kind of lenses. This is from a long time ago, 2004. These days, the designs are simpler with many, many, many more aspherics. This only has 3 aspherics and about 30 lenses. These days, they have maybe half as many lenses, but maybe 12 aspherics. And by using lots of aspherics, they can make the weight, the size, the heat absorption. There's a lot of advantages. So this is like a really ancient kind of design, but that's what I've been doing. The distortion budget is at 1 nanometer over about an inch field of view. And the waveform quality this is also out of date. Now they get about 2 milliwaves over the field. Those lenses are made by Zeiss and then put into an ASML machine. You see it's vertical so that there's no gravity deflection that would be asymmetrical. And this is some years ago. They sell for $20 million a piece. And Zeiss has made maybe 1,000 of those at $20 million a piece. So it's a big ticket item. But in 2006, about 11 years ago, I invented a new kind of design that combines mirrors and lenses that allows much higher performance. And those, which are, again, it's about 1 meter long, about this big, those sell for about $50 million each. And they can't make them fast enough. There's huge demand for these things. And all of today's state-of-the-art computer chips are made using my design. It's an immersion design, very high numerical aperture. Unfortunately, I don't get a penny out of this because my arrangement with Zeiss is they own all the ideas I come up with. I mean, they pay me, but I don't get a royalty or anything. And this is a typical example of, it's got some mirrors and a whole bunch of lenses. And with the latest version of this lens mirror design, on one of your red blood cells, you could put at least a 30 by 30 image. It's amazing to think of the nano size of things. And even more recent is X-ray lithography, and I've done a whole bunch of mirror designs for that. What's beyond belief is that for these super-duper optical systems, the surface accuracy, surface roughness, is about 3 to 4 times the diameter of the hydrogen atom. So those surfaces are made, and they're highly aspheric, not a little bit, like many millimeters of asphericity are being made to an accuracy that's atomic level. You can see why they cost $50 million each. I've also done work for KLA 10 Core, making some extremely broad spectral range systems that have only one glass type. This is all silica, and yet it works over an enormous spectral range. And Olympus has made a prototype that could be used as a microscope for laboratory. So my plan, I did my early years, my middle years, and my future. My plan is I'm going to work forever, but with fewer hours, and after death, I plan to cut back to about 20 hours a week. And I love this cartoon. Relax, honey, change is good. So that's it.
Questions?